Hello again. Welcome back. This is Notes 3B about fission. So the first thing I want you to do is pause the video and use the word bank down here to answer the thing up there. Fill in those blanks. All right, welcome back. So the source of energy that sustains life on this planet is the sun. And the energy from the sun comes from the burning of the gas hydrogen. Energy is also created from the fusion or combining of hydrogen nuclei into new substances, such as helium. The helium can then combine to create beryllium, and adding more helium creates carbon and then oxygen. All right, pause that if you need to get those written down. So yesterday we learned about nuclear fusion, which is the process of energy being created by the combining of nuclei in stars. So today we're going to talk about the opposite process called nuclear fission. So they're both nuclear. They're both involving the nuclei of atoms. But one is fusion, where two small come together to make a larger one. This is fission, where one large gets split. So we've got a picture here of what happens in nuclear fission. So you've got your target nucleus. It's usually going to be a uranium atom, and you send a neutron at it, and that neutron makes it just too heavy. It's like if you were carrying the laundry for your mom out of the dryer, you didn't have a basket, and you're getting up, and you're just barely, and she puts one little sock on the top, and that's it. You just drop everything because you can't hold it. Just that one little sock was enough to make it all fall. That's basically what happens here. Or like, that classic Christmas shopping cartoon, the father's walking around with all the packages and the mom adds one little box and he drops everything. That's what happens in fission. You've got this nuclei that's not very stable. And then so you add that one little bit and that's it. It's going to break apart. So we're going to do our own version over here because there's something they are missing. There's a very important part of this that they don't have. So they have the neutron, and we do need that. We need our neutron being put in there. And then we've got our large unstable nucleus. So this is going to be uranium. All right. Now, when that neutron hits that nucleus, energy is released. And that's the most important part. And they left that out. So we're definitely going to fix that. But we do get neutrons. There's random free neutrons that are just flying around. And then we get two smaller atoms, barium and krypton, normally. All right, again, pause it if you need to, but I'm moving on. In nuclear fission, also known as radioactive decay, a neutron is aimed at the nucleus of a large, unstable atom, like uranium, thorium, or some other radioactive element. The extra mass of the neutron causes the radioactive nucleus to split apart, forming smaller elements, free neutrons, and lots of energy. The free neutrons slam into other radioactive nuclei, which continues the process. It's kind of like a chemical reaction. The chemical reaction is going to keep happening until all of the reactants are used up. Same thing here. A nuclear reaction is going to keep going until all of the unstable nuclei are split. Until all of the energy are spent and the larger atoms are split into smaller elements. This process causes so maybe you don't remember back to sixth grade, but think about back in sixth grade, what was when you were learning about the layers of the earth And the very outside of the earth had the same name as in a pie, and it's called the crust. Well, guess what? Yet again, they've oversimplified things for you. If you get higher up in science, you will know there is no such thing as the crust. There is the asthenosphere and the this sphere and the that sphere, and it's there's nothing that we call the crust. But you know that beneath the crust, there's that layer that you were taught outer core and outer core, inner core, and mantle. And yeah, the asthenosphere is the lower part of the crust and the upper part of the mantle, and that's where we're talking about this stuff happening. So there's a thing called convection. So maybe somebody has a convection oven. You've ever heard of it before? Convection ovens cook fast because they move air around. So this process of the uneven heating and cooling of the rock, where fission is happening way down deep inside the earth and it's melting the rock, and then that hot rock rises, and then the cooled rock that was up here sinks, and so you get this motion like this. So because we have this circular motion, you can end up with the plates, the tectonic plates that are floating on top, those crustal plates, not crust, they'll move away from each other, or they'll slide past each other, or one will be driven under another one. And when that happens, it melts, and then a bunch of pressure builds up, and then we get a volcano. And when they slide past each other, they are trying to slide, but it gets kind of stuck, and then like all of a sudden, boom, it moves all at once, and that's a earthquake. So that's where we get the energy for volcano. Oh, I'm messing it all up. That's where we get the energy to cause earthquakes and volcanic eruptions. So if it wasn't for fission happening deep inside the Earth's crust, we wouldn't have earthquakes or volcanoes. And these are naturally occurring examples of fission. All right, again, pause it if you need to, but I'm moving on. Nuclear fission is also because of the energy created in nuclear power plants and in nuclear bombs. Because fission involves the splitting of harmful radioactive elements, it can be dangerous. So if we lose control of the processes involved, it can lead to radiation exposure, which can be fatal. So you can get exposed to a fatal dose of radiation. Going once, going twice. I'm just pretending like you're in class. All right, so you got a lovely little picture here. The first thing I want to point out is this thing. This is the thing that most of y'all associate with nuclear power because you've seen it in The Simpsons and all that stuff. First thing you need to know is that thing's not required every time. For example, the one here in Virginia, Lake Anna, doesn't have one of those. It has Lake Anna. The other thing you need to know is this is steam. It's water vapor. It's not smoke. It's not polluted air. Nothing's burning. That is literally, it's just water vapor. It is steam. So really, nuclear power plants are just cloud factories. This is the building where the actual business happens. And I want you to notice the shape of the roof. They designed that on purpose. It's to help for safety's sake. If something happens, that shape is much safer. And then notice how thick the walls are. So those walls are like 20 feet thick concrete with lead sheets inside of them, so that if something comes out of containment, it stays in the containment building. That's literally why it's called the containment building, to contain the processes. All right, so there are pros and cons to nuclear power, and you need to know them both. So here we go. Pros. It produces vast amounts of energy, like a lot, like an amazing amount. It does not produce particulate air pollution. So when you burn gasoline, diesel, when you burn leaves, when you burn coal, when you burn anything like that, there is particulate air pollution produced. So when we burn, what was 2 lines? fossil fuels. Duh. I just said it. When you burn any fossil fuels, you're going to get particulate air pollution, and there is none. There's no air pollution. It fuels about 20% of the electrical energy of the United States. It produces more kilowatts, which is how we measure electricity. It produces more kilowatts of electricity for fewer cents per kilowatt. So it is cheaper than all of our other things. Coal, wind, solar, it's cheaper. And it is considered to be safer than the coal burning plants in the US. There are accidents in coal mines and in coal plants all the time. You hardly ever hear about accidents in nuclear power plants. And when it does happen, very rarely are there any deaths. People die in coal mines. It's not good. It's really not safe. Now, notice I said in the US, because nuclear power is very highly regulated in the United States, it is safer in the United States. Can't speak for other countries because all other countries don't necessarily have the NRC on their side, the Nuclear Regulatory Commission that keeps everything straight. All right, what about cons? It involves the splitting of harmful radioactive elements. So you've got to be careful. It's dangerous stuff. If you lose control of it, you will have radiation exposure. So there have been times that control has been lost and people were exposed to radiation. It does produce a radioactive waste product that has to be stored. Now, that's only because the U.S. is stupid. I don't really have time to talk about it here. If you come to class, I'll talk about it. But send me a message if you want to know what I'm talking about, because the U.S. is just dumb when it comes to this. Anyway, the cost of building the plant isn't taken into account. Okay, so over here where we said it produces more kilowatts of electricity for fewer cents, so it's cheaper. That's only in the actual production of the electricity. The cost of building the plant is not factored in, and they are pretty expensive to build. But what's great is once they're built, they stay commissioned for years. Plants that were built in the 60s get checked up every 10 years or so. And as long as they pass inspection, which because they were built so well, they do, they keep on running. They don't get decommissioned. So, yeah, it costs a lot to build it, but it lasts. When it's not properly contained, so when you don't have the concrete walls and the dome structure and the lead inside, it is a huge safety risk. And one of our big examples of this is Chernobyl. Now, at the time when this happened, it was part of the USSR. Now it's in the Ukraine. The Ukraine is separated from the USSR and it's its own country. But in the time this happened in the 70s, Chernobyl was part of the USSR. And you can Google it for yourself. You can look it up. But Chernobyl was a really terrible accident. And I think one of the biggest, I know that one of the biggest problems was they were in an office building. They did not have a proper containment facility. If you Google pictures of Chernobyl, you will see that the building was a big rectangle. And it's not these big, thick concrete walls. It's just a regular old office building. Check it out. You'll see what I mean. So when there was a problem, it didn't get contained because they didn't have the proper containment unit. All right, again, if you don't have that, pause it and go back, get it written down. All right, so we're going to compare and contrast fission and fusion. So we're going to put fission on this side and fusion on that side. Now, I do challenge you to pause this now and at least try to think of a couple of things on your own, but just in case, here we go. So what do they have in common? Lots of energy. Makes vast amounts of energy. Like a lot. It's really kind of amazing how much energy. And then the other thing they have in common involves the nuclei of atoms. That's how we know it's called nuclear, because it involves the nuclei. All right, so what about fission? What's our definition of fission? Fission, split. It splits apart. And then what does it mean to fuse something? To join or combine. In fission, we have one large atom that gets split into smaller ones. In fusion, we have smaller atoms that get combined into a larger one. So one large atom splits into smaller ones and lighter, really. I'm going to put lighter instead of smaller. And over here for fusion, we have two small atoms combine into a heavier atom. All right, where is fission found naturally? Where is it? The natural energy is Earth's core energy. So it's the reason why the core is so hot is because fusion is taking place in the core. And we know that fusion, the energy is from the sun. That's how we get our energy here on Earth, is from the fusion in our sun. What element is mostly involved in fission? Uranium. What element is mostly involved in fusion? Hydrogen. And last but not least, something random, a fact about each. So in fission, radioactive waste is produced. There is no radioactive waste produced by fusion. Fusion, our extra little hint is going to be that this one's the one that has stupidly high temperatures. Temps over 100 million degrees Celsius. All right, again, there is a video that we watched in class that I'm going to put the link to in today's folder, so hopefully you'll check that out. I guess that's it. Have a lovely day. Make good decisions. Bye.